And we're ready to rock and roll. So, hello, Roomers, Zoomers, happy garbage day to everyone, otherwise known as Tuesday. So we have several things to chat about. First off, we have formative assessment number 4, we have homework 4, we have the remainder of lecture 4 and example 4B, and then potentially lecture 5 as well. So how about we start with homework? So let me get my screen share going so we are all on the same page here. And I will open it up to any homework questions so far. Due next Monday, so you've got a week or so to work on it. Those of you who've started this, how's it going so far? So far, so good. We had questions about log likelihood and ratio, likelihood ratio tests. What was your question?
I actually already get the mixture p-value correct. The likelihood ratio test will be double of the mixture one, but the program still tells me the answer is incorrect.
Okay. Are you entering the difference in -2 log likelihood to 2 decimal places?
Yes.
Okay.
Actually, it's 1, 2, 3, 4, 5, 7 decimal points.
Okay. No, it wouldn't be a problem. 7 decimal places is more than sufficient. It will round it. It's only checking to 2. So as long as you've got it to that level of precision, then it should work. Are you making sure that you're using -2 log likelihood as opposed to log likelihood?
Yes.
Okay. Then that exceeds what I can troubleshoot in front of everyone. But if you want to send me a screenshot of what you've done and what you think the answer is, I can check it against the database.
The mixture is already correct. The likelihood ratio will be just a double thing, right?
The mixture p-value is correct, but the test statistic is incorrect?
Yes.
Okay. Then it's possible, so for a mixture p-value, just to review folks, if you compute a regular p-value for a chi-square with 1 degree of freedom and cut it in half, that gives you a mixture for a chi-square of 0 and a chi-square of 1, which is appropriate anytime you're testing a new parameter that's on the boundary. So the null hypothesis is that it's 0, which is also the lowest it can be, and that's the type of situation in which you need to worry about using a mixture instead of a regular. But likelihoods have been the one thing that has worked consistently across packages. And so I don't think it's necessarily a R to SAS to status sort of issue, but if you can send me what you think it is, I can help you figure out where the discrepancy is. And that goes to anyone. Remember the rule, 15 minutes? If you get stuck on one problem for more than 15 minutes, you stop. You send me a screenshot. Because I can look up the answer and I can tell you what happened. Either if the problem's on my end or your end. Either way, I can help. Okay. And for those of you using Stata, just a reminder that to compute the Pearson chi-square over degree of freedom statistic for conditional distribution fit, you'll need to use n as your denominator instead of n minus k. And I put in code in example 3 when I was building this homework, and it's inside the instructions right here for what the Stata command is to generate that piece of output for you, so you don't have to do any math. All right. So no questions other than that on homework?
I have a quick question. So,
okay, 2 more then. Go ahead, Nathan.
When we're creating the attributes in the paragraph below that, is it greater than or equal to 1 or just greater than 1? For the second.
For the second one? So the slope basically should be coded such that it indexes anything past 1, so 1 session would still be coded 0.
Okay.
So there's basically one predictor that differentiates attendance at food school of any kind from 1 session, so no versus 1. And then 1 from 1 on is a continuous slope for the number of sessions. We have, let's see, okay, another question about moderation. Okay, what was your question, Chen Chen?
Yeah, I want to know in section 2 how many predictors in the model.
How many predictors are in the model?
Yeah, that because I think we have older siblings
Mhm.
and the younger siblings and both parents work.
Yes.
And then we have two new predictors, whether the attendance and whether the attendance has the one, and then we have two more interactions.
Yes.
The interaction between both parents' work and do they attendance, and the parents' work and do the attendance plus one.
Yes.
Okay.
Yes. Okay. So I don't know if you all heard that. We're checking the number of parameters in the model here. So we have presence of an older sibling is a binary predictor. Presence of a younger sibling is another binary predictor. Whether or not both parents work full-time is yet a third binary predictor. And then we have two slopes for the effective food school, 0 versus 1, and then past 1. And then I wanted to know whether the effective food school, so these two slopes, whether they are significantly moderated by whether or not parents work full-time. So the research question would be, is food school just as effective in children whose parents work full-time as parents who do not work full-time? That's the idea. And Andrew, you had a question with moderation?
Yeah, I know we've obviously been over this before about like you need to include both the interaction term and the term itself if they're both like turned on or like if they're both like the one in the binary. But I was just still messing it up, but maybe we're gonna go over that with the examples again anyways.
I didn't have any other moderation ones beyond just example 3, but I can pull that up if that would be useful to go back over.
Could we just do like one, like one example of interpreting a model?
Yeah. Yeah, let me get, I'll just pull up something to type with here. So we have, the outcome is number of things tried. We've got beta 0. Do you all remember how to do this, by the way? How to make equations in in Office products? What I typed to get this started was Alt and equal to insert equations. And then once you're inside the equation, you can type the name of the Greek letter with a slash in front of it, the one that's above the Enter key. And then it jumps to become that Greek letter. And then an underscore for a subscript. And then you hit space, and then it jumps in like that. So let's just do, we'll call this any for food school. I think this is what I named my slopes here. Beta 2. And we'll call that, no subscript, no I's in this class. There we go. And then I'll just throw in the predictor that interacts with it, because the others will drop out with respect to the moderation terms. We'll call this full-time, like that. And so then we have any times full-time plus, this will be beta 4. So this is not exactly your analysis model. I'm leaving out younger and older siblings, but that's because they're not involved in the moderation, so it doesn't really matter. So this is basically the model for the means thus far. So then if I want to know, everybody get to the left here. No? All right. I don't know why it insists on putting things in the middle when I asked for it to be left-sided. There we go. There we go. Okay. So then if I want to know what the slope, say, of full-time is, what's the rule? What do I do first? Okay, say it louder. We got to hit the microphone.
When you extract all the
find everything that has full-time in it. So this will probably be easier if I just type. Come on. So we got beta 3, and we've got beta 4. Nope. Typing in front of people is the surest way to get yourself typos. And beta 5. Oh, wait. Need to fix this. Amount. Yeah, see, I can't type it all in front of people. This is why I don't do things on the board or live very often, because I do not trust myself to be able to have basic skills. Okay. So we have the ingredients here. I've already extracted out full from all of these. So this part right here is how we make the slope. So the ingredients for the slope, so to speak, that you would feed into an estimate statement in SAS, a LINCOM statement in Stata, or a GLHT statement in R. So full-time at what food school? Yes, exactly. So the key thing to get these slopes right is that the slope itself for whatever the predictor in question, it always gets a 1. So at a minimum, to get the slope that differentiates parents who work full-time from parents who do not, I need 1 beta 3. Now, given the way the model is coded, if I just have beta 3, who is that going to be the slope for? What kind of child? Say it louder. Yeah, when this is 0, meaning they never went to food school, and if they didn't go to food school, they don't have an amount. So, yep. So then if I want to get, say, the slope for somebody who went to 1 session and never went back, then I need to put a 1 here. And what goes here if they only went to 1 session?
0.
This drops out at 0, exactly. If they went to 6 sessions, what goes here?
1.
1. What goes here?
5.
Yeah, it's the number of sessions past 1, so a 5 would go here. And when you're building your model, in R especially, watch for the order of the fixed effects as they come back out, because that's the order that your coefficients have to be in for the GLHT to work. And it automatically reorders them so that all of your main effects are first, followed by any interaction terms. So if you wrote it in a different order, then that might be a cause for why you wouldn't necessarily be getting the right answers, is because the order depends on how it wants it to be. So then if I do something like slope of any food school, it's the same sort of idea. I need beta 1 at a minimum, plus beta 4 times full, plus, that's it. So beta 1 would be the effect of going to any food school in what kind of kid? Yeah, parents who don't work full-time, when full equals 0. And so then this is essentially a switch that turns on the slope for parents who do work full-time. So the sum of these two then gives you what the slope would be to differentiate the effect of going to no sessions versus 1 session. And then the same thing would be true for amount. Where we start with beta 2, and this switches to beta 5. To get predicted values, we need everything. So the very last questions in, I think, section 2 ask for predicted counts. So the first step is to figure out what is the predicted log count according to the model, and then to inverse link it. So that would be ilink in SAS, margins in Stata without the pred xb, and then in R it would be type equals response. We have a comment, taking notes as you explain. So in your estimate Lencom statement, put a 1 in place of the slope for the predictor. You want the slope 4, correct. And values of the other predictors in place of the interacting slopes, accounting for centering and careful with order. All correct. So keep in mind that when you see these sorts of statements, it does get very tricky with categorical predictors. So like when you write out the name of the variable for full, for instance, you are not referring to the variable. You are referring to the beta the variable is to get in the model solution. So if I want the slope for full time, and one of my ingredients is this interaction term here, full, that has already been given a 1. The value that I fill in is for the amount. So the value that you fill in for the interaction term is always for the moderator, because you've already got the slope figured out. Okay. Other things that I can go over or help review. So if it helps at all, the story behind this assignment is that at food school, they tell you that you're supposed to present like the same food like 15 times, and eventually your child will try it. Well, guess what? We have very little time to work with the picky palate of a 4-year-old if your parents both work full-time. So it turns out that in my story here, food school is going to be less effective in children whose parents work full-time. That's my hypothesis that drove the story here. But as usual, your particular results will dictate what the correct answers are. So if you want help with the coding, visit example 3, because that was an example in which we had a moderator that was dichotomous, just like full-time is, and it took 2 slopes to differentiate the effect of emotional regulation condition, just like it took 2 slopes to differentiate the effect of food school. So the variables in the story are different, but the structure is very much the same. Okay, other questions I can help with respect to homework to start with. All right, and again, 15-minute rule. If you get stuck, let me help you. All right, so that one's done then. I did put up, let me see here, looking at reminding myself. I did put up a new lecture. I sent an email out today. I am working on example 5A, and it is close to being done. I was happy to be able to figure out R for this, and I only almost cried once. So that's like an improvement in my R code to crying ratio. It's getting better, a little bit slowly. Okay. Now we have formative assessment number 4 to go over. Are we ready to talk about this? All right. So I read everyone's answers this morning, and I feel like for the most part this went pretty well. I do see a couple of opportunities for clarification. So what is the role of a log link, and what kinds of outcomes would you choose a log link instead of a logit? So who wants to be brave and tell us what you wrote down?
So is that use a log link when it's only bounded in one direction, and then the logit link if there are 2 boundaries? Is that correct?
That is absolutely correct. So a log link, the first instance that we saw of that was for count data. So counts have a lower boundary at 0 and no upper boundary. They're discrete. So counts are modeled with Poisson, negative binomial, or some flavor thereof. And also in the last unit, we talked about positively skewed continuous outcomes. Same issue. So if you have something like response time that can't be 0, if you have something like house prices that can't be 0, but it's positive, so it's positively skewed, meaning there's likely to be extreme values on the upper end, a log link can help to keep the predicted outcomes from going negative. So a log is sort of a general, all-purpose, bounded at 0, skewed continuous, or discrete from that point forward. And then the logit, or as Jonathan kept saying in his talk, log odds, because that is probably the more common way to talk about it, the log of the odds, that is for 2 boundaries. So the first instance we saw of logit was for binary outcomes, just 0 versus 1. Then we saw logits for categorical outcomes. So just as a review here, how is it that we can use a logit to model something like a Likert scale response from 1 to 5? How does that work? Ooh, almost spilled my Mountain Dew. Party foul.
Is it because you can't answer lower than lower than 1 and higher than 5?
Mm-hmm.
So
Same
you
idea.
need to bound or remove. Yes.
But do we
I
have
think
one
you cut
more?
out on the question.
Oh, okay, thanks.
What was the full? Yeah. Or at least for me.
Yep, let me see if I can shut anything down here and get some resources back. I'm even at school, so it's not even like my home internet that I can blame on this today. So the question was, how is it the case that we can still use a logit link to predict an outcome that's bounded between 1 and 5 as opposed to bounded between 0 and 1? So just trying to do sort of some big picture review here. How does that work?
I would say that we can use proportions.
You can use proportions, but if you have something that's like an ordinal variable,
Yeah.
how does the logit work in that context? This is like a month ago.
Yeah.
You learned this, I swear, you did.
Yeah. I would use a cumulative link function.
Cumulative link function. How does a cumulative logit link work?
It compares the upper and lower part. It is divide the categories into submodels, comparing the lower part with the upper part. So, for example, in this case, the first submodel would be something like, what is the probability of having a 2, 3, 4, or 5 instead of 1, and so on.
Yes, so we're taking an ordinal outcome, and we're using a number of categories minus 1 binary submodels. And so then the logit predicts the probability of being in the upper category as opposed to the lower category, where if I had 5 possible categories, it would be the logit of 1 versus 2, 3, 4, 5, 1, 2 versus 3, 4, 5, 1, 2, 3 versus 4, 5, and then 1, 2, 3, 4 versus 5. So it's still binary, and that's why the logit works for Likert scale type data. And then as a tie-in, for those of you in IRT land, what is that model called?
Graded response.
That is the graded response model. So it's the proportional odds version, by the way, because you get one slope per item that is shared across the submodels in the same way that predictor slopes are shared across submodels when you're predicting an ordinal outcome. And same premise, if you have a nominal variable, we can still use a logit for that because you would have one category outcome as the reference, and then you would be modeling the probability of selecting each other category in each separate submodel. And do we care about probits? Remember the deal with probits? No, probits and logits basically do the same thing on a different scale. The logit is the log of the odds of the probability of a 1. The probit is the z value that corresponds to that probability on a standard cumulative normal distribution. But they're both symmetric link functions. If you want something that is asymmetric to predict an outcome that's bounded above and below, then that would be like complementary log-log or standard log-log. And then what other kinds of outcomes besides binary and categorical do logit link functions work for? What we just finished talking about, actually. Zoomers, am I still there? Okay. Just awfully quiet on the Zoom.
Is it inflated and hardened models?
Say it louder.
zero inflated and hard models?
Yes, logits are used in zero inflation models. So we will, let me put a pin in that one because that's the next question. But I'm looking for another kind of outcome type that would use a logit link function to solve the issue of being bounded above and below. Binary is a special case of it, but there's only one trial.
And dichotomous items?
No, dichotomous is the same as binary. Binomial, yeah. Andrea, I saw your lips move.
I said the wrong one, though. I always mess up Bernoulli and binomial. Far
Yeah.
about it.
So Bernoulli is binomial with one trial. So you're not wrong. It's sort of labeled binomial in a more general sense, but I make a distinction when I teach them because in Bernoulli, there's only one possible conditional distribution and that's it. Whereas binomial, there's lots of choices depending on how variable the proportions are. So predicting proportion correct, you can use a logit link or a probit link or a log-log for the same thing, bounded above and below. Yep. So log link, summarizing, is for bounded below but not above. Logit, probit, etc. is for two boundaries, generally speaking. So any questions on that one? Okay. So what kind of outcomes would Poisson and negative binomial be appropriate choices? Counts, yes. So these are discrete distributions. So you cannot use them with things like response time or house prices that are continuous and take on non-integer values. So counts is the example that we have. And then two concerns with respect to zeros. What are they? Yep, one of them is if there are no zeros, what do you do instead? Yeah, so the zero issue is none or too many, broadly construed. The none issue, if you don't have zeros in your count, if one is the lowest count that you have in your context, what do you do about that?
Use a zero altered distribution?
Yeah, so these two have zero altered or zero truncated. Those are the key words to look for. And they basically rearrange the likelihood so that it still sums to 1 without the zero involved. And no, you cannot just subtract 1 and use a regular Poisson. It doesn't work. I tried that. Because that was the first thing. I'm like, oh, I can fix this. I'll make some zeros out of this. No, it doesn't work. So yes, that one is that's a little more straightforward. Now the extra zeros, we've got some comments here. Mini models for too many or submodels for too many. Yeah, tell me about those. You've got two flavors of what to do with extra zeros.
One is a hurdle.
One's a hurdle. What's the other called?
Zero inflated.
Yeah, zero inflated. Good. Now the difference between the two. What's the difference and how they address the extra zero issue? What does a zero inflated model do?
Is that probably being an extra zero?
It models the probability of being an extra zero as a separate submodel. So you still have your regular count regression where you have Poisson and negative binomial with zeros in it, but then you also have a separate submodel by which you can allow the presence of extra zeros. And you can do a likelihood ratio test as to whether or not that submodel helps improve fit. And the tricky part of that is that zeros are in both submodels simultaneously. So even though statistically we're making this distinction about whether we have extra zeros, I don't know on the ground how I would talk about a slope that predicts the probability of being an extra zero when you could also be a regular flavor zero at the same time. That's where my head starts to hurt. I don't know that there's an easy interpretation that goes with that. But I would go with zero inflated if you just need to account for there being extra zeros, but you're not really interested in predicting why or how or where. Just let them be there, so to speak. The alternative then, the hurdle. Yes, if zero, and then if how many. So I call those if and how much models, generally speaking, where you cut off the zeros. and you predict whether or not it's 0 versus something in one submodel using a logit, and then how much something if not 0 in a second submodel using a Poisson or negative binomial that's 0 truncated. So that's the kick. The hurdle models, you have to find a distribution that takes the 0 out of the amount part. Which is why I lump these two together, because if you're aware of the idea that there is this 0 altered or 0 truncated count distribution for instances in which there are no zeros naturally, you can borrow that technology to fit your hurdle model if you take the zeros off and treat them as a separate. So when I would do hurdles in practice is when I'm dealing with a count outcome that is conceptually both kinds and amounts. So if you have a questionnaire, for instance, like number of victimization experiences that you've had, something like that, where you would have people in the study whose characteristics do not lend themselves to victimization and people who unfortunately have had that happen to them. You might predict whether or not someone's been victimized as one outcome, and then how severe of a victimization, if so, as a separate outcome. To me, that's a lot cleaner to interpret. It's just a little bit trickier to estimate because the 0 altered distributions are harder to find. Okay. Questions on that? Or any that you want to hear again? Nathan?
So when we're doing this in the computer, does the computer apply the link function to the conditional mean of the outcome and then fit that to the distribution that it's being told to fit it to? Or, because I don't know, I think it's probably just a wording thing in my brain, but like, are the conditional distributions reliant on before or after the link transformation is what a simpler way of saying it.
Okay, if I understand your question, is it if you pick a certain conditional distribution, does the link automatically go with it? Or are they sort of separate?
So like if you, so if we were to do this by hand, which we wouldn't, but like...
You say, I'm going to stop you right there. There is no likelihood estimation by hand.
No, but like, so, but you wouldn't want to walk in just automatically assuming that I'm going to use this conditional distribution without seeing how the residuals are, right?
Okay, so it is true that all of the assumptions that you're making apply to the residuals and not the outcome.
Okay.
However, the type of outcome that you have and its general shape, I think, point you in a direction of possibility.
Okay.
So it's not like you'd have to try every single generalized model you've ever heard of every time. It's like, okay, this is within a binomial family, or this is within a categorical family, or this is an account family, or this is in a continuous family. And then from there, it's like, can I get away with normal, or do I need to switch to something else? That's heading into the next question. But
Okay, that makes sense.
when you look at it in software, there are certain combinations that are sort of yoked together, and it may make it seem like you don't have choices, but you still do. So like if in Stata, there's a logit package that automatically fits a logit link and a Bernoulli distribution. In the Poisson package, it automatically fits a log link. So there's things because it's convenient and it's like what people typically pick, but you're not stuck with those combinations. You can still make a custom arrangement if you need to.
Okay.
But yeah, they're two different things. The link is used to keep predicted outcomes within boundaries, and the distribution is used to describe the variability of the residuals.
Okay.
And whether it's constant or non-constant with some specific pattern to it. Getting ahead of I think that's the last question, but we're heading that way. Okay, other questions or things that you want to review? Okay, so then same idea on question 3. For what kind of outcomes would binomial beta or beta binomial be appropriate for? What are these for?
Double bounded outcomes.
Yeah, double boundaries. So proportion correct, number incorrect, and potentially scale scores that have ceiling and floor effects. I would think of those as a special case of these as well. And with respect to zeros and ones, We'll make this a yes-no set of questions. Does the binomial distribution allow perfect scores? Like all of them correct or all of them incorrect? Yes, it does. Does beta?
No.
No, it does not. How about beta binomial? Yes, it does. So even though it's called beta binomial, I think a more correct way to think about it is that it's based in binomial and there's a beta add-on. So it has the properties of binomial in that it's predicting inclusive of 0 and 1 if it's a proportion, or 0 correct or all of them correct, which is an amount that you determine with a variable in your data set. But then it allows the variability to exceed what's predicted from just the mean. So the way that it's described in your textbook is that the binomial parameter p, that is the conditional mean of the distribution, follows a beta distribution itself. That's the way that it's written. That may help you. It doesn't help me too much, but that may help you. So it's based in binomial, but there's an add-on that allows extra variability as a function of the mean, as a multiplier. So then zeros and ones, same issue. You may have extra relative to what the model predicts. And so this is where we would have the same sorts of options. A 0 inflation or a 1 inflation would keep the 0 and 1 if it's inside the binomial already and have extras potentially. Or you can switch to a hurdle where you cut them off and put them in separate submodels. The latter is going to be harder to find because of the need to keep a distribution that doesn't have those. Like, I don't know of a 0 truncated binomial, for instance. I don't know if that's a thing. Maybe you could make it up if it's not, but. So these ones are a little bit trickier to use in practice. Okay, question?
So is that possible in programs to kind of make your own custom distribution, conditional distribution? Because
I think so.
it makes sense, like in my head, it makes sense with link functions, because that's just transforming, but like, I feel like it'd be really complicated.
Well, I think that any distribution that exists, so like if the math is out there and it's just not in software, then you certainly can. You would just have to find a routine that allows maximum likelihood estimation of a custom object, essentially. So in SAS, you can use proc NL mixed. I think there's like MENL or something like that in Stata. I'm trying to remember the name of it. I'm sure there's something in R. I don't know what it is off the top of my head. But you're sort of in that same world if you switch to Bayes estimation, Bayesian estimation, because then you have to sort of program everything and you can make a custom thing, a likelihood to be maximized. So Bayesian estimation, by the way, does rely on maximum likelihood in exactly the same way that we're doing in this class. The difference is the use of a prior distribution for each potential parameter to be estimated. If you choose what is known as uninformative priors, so like basically each number could be anything, then the results will asymptotically be equivalent to what would you get at a straight maximum likelihood. So Bayesian isn't different. It takes what we're doing in this class and adds to it, is the way that I would think of it. And the reason you would do Bayes is if you want to accumulate evidence, so you have, like, say, prior studies that describe what a parameter should be, and you want to include those prior studies, kind of like what people do for election forecasting. If you're having convergence issues would be another reason. So tightening what a parameter could possibly be can make a model converge when it wouldn't otherwise. But everything that you're learning for I would say everything or almost everything translates to that context, but you can learn more about that in the fall. All right. Other questions on question 3? Okay. Now this one. A variety of answers on this. So how do the generalized linear models we've seen so far address or not address the typical assumptions of linear regression? So generally speaking, in statistics, when you fit a model, your assumptions are that model. So when you order, say, a standard linear regression, you are ordering a residual term that's supposed to be normally distributed, have constant variance, and be independent across observations. It is not true that linear regression assumes linearity. It assumes whatever you tell it to assume. So if you take a slope and you fit the slope, and then you take the predictor squared and you fit a second slope to get a quadratic effect, then the model is assuming a quadratic relationship between your predictor and your outcome, not linear. If you take a predictor and you log transform it, and you fit a linear slope of a log transform predictor, that is a cheap and easy way to capture an exponential relationship instead of linear, and then the model assumes there's an exponential relationship between x and y. So the model assumes whatever you tell it. It's like, what did you order? That's what it's supposed to be. So by changing the model, for instance, if we're saying, we're not going to use the normal conditional distribution, we're going to use Bernoulli, we're going to use multinomial, we're going to use Poisson, we're going to use negative binomial. We're changing. Then we assume that it follows that distribution instead. So we're no longer assuming normality if we didn't order it. Independence, yeah, let me get through constant variance and then we're going to do the independence because that's the one that I was going for here. Constant variance. The only distribution that assumes constant variance with it is normal. Everything else says variance is some function of the mean. And you can actually order variance that is a function of the mean within the normal distribution too. So within SAS, for instance, in their mixed package, there are options for what you can do with the residual variance, where you can have it vary as a function of predictors. So you can say that as x goes up, the residual variance goes up. You can also have it vary as a function of the mean. So it's called a power of the mean model. And I think there may be linear or quadratic versions of that. So you can put non-constant variance in any kind of model that you want to. In the combinations of the distributions that we've been working with, though, most of them don't say it's constant variance. Most of them say it's either variance that's directly tied to the mean or is some scaled function of the mean where we estimate the scaling factor. So that's like negative binomial where we have that stretchy factor, beta binomial that has a stretchy factor, those kinds of things. So these are the two that we've been working with this semester. Now the big one, independence. Have we done anything that you can think of that changes that in this class?
Not yet.
We have not. Yeah, so that's where the second half of the class is, I guess not quite second half. I go last third. We're at 5 weeks. 5 weeks till the end, folks. Hang in there with me. 5 more weeks. I know it sounds like a lot, but we're on the downhill slide here. If you have outcomes that are related to each other, so outcomes from the same person, from the same group, or otherwise, if you don't have independent residuals, we need a different kind of model altogether. So that's where we would enter the world of what I refer to generically as multivariate models, where the big difference is that the likelihood function has as sort of its core for each person a set of residuals, not just one. So you literally build in the expected correlation between the residuals into what your model says should happen with respect to your data. And there's 2 different ways to do that. One is directly. So you can just say, hey, let the e's from the same person be correlated, okay? And it says, sure, your correlation was estimated to be 0.8 or whatever. Cool, thanks. That only works with normal distributions. If you have not normal distributions, or if you have multivariate structure that's a little more complicated, then the alternative is random effects. So random intercepts and random slopes. What they are for is to introduce correlation and heteroscedasticity into your residuals. So we will do a little bit of that in this class, but then I hope that you will come back. If you haven't already had the other clustered multi-level models was offered last fall. I'm supposed to be doing longitudinal multi-level models this fall, and then hopefully an advanced course, an advanced longitudinal in the spring, maybe, if I can swing it. But that's what those are for, multivariate cases that are more complex in terms of their structure. So yeah, we haven't touched independence yet. All right, how are we doing?
Lisa, quick question. This advanced longitudinal class would be spring 2023?
Yes, if I can swing it. It's like, it's a degrees of freedom problem. So I'm hoping that Ariel may pick up the intermediate stats class so that I would have room in my schedule to do it.
Got it.
That's the tentative plan. So, because I used to teach a 2-semester sequence at both of my other jobs, at the University of Nebraska and at the University of Kansas, and that worked so much better because we actually had time to get into time-varying predictors and multivariate longitudinal models and link functions and 3-level models and cross-random effects models for people who change groups over time and all kinds of stuff like that that I don't have time to get into in just 1 semester here. So fingers crossed, I will be bringing back what I used to call 945 in a year from now. We'll see. And if not, it lives on the YouTube, so you can have the old stuff. It's just that there's no R there. Anywho, other questions? So Farhan, let me answer your question. Need MLM for independence, otherwise generalized is cool. Yeah. So what if I have, say, students nested in teachers and I want to predict a binary outcome? Then I need everything we did this semester plus everything that you would do in a multi-level modeling class at the same time. So just as there's multi-level models, there are generalized multi-level models that solve the exact same set of problems. And interestingly enough, it's always the lowest level residuals that change their distribution, not the random effects. Random effects are almost always multivariate normal. If Bayes and frequentist analysis disagree, which would you go for? Oh, Farhan, you love to ask me 3-bear questions, don't you? So that's an expression that means it would be in the context of a longer discussion. Like it would take 3 beers to go through the full set of like possibilities. Not that I'm drinking in front of you. I promise there's nothing in here but just regular flavor caffeine. But meaning that's a longer. So here's my issue with Bayes. The way that I appreciate it is that Bayesian estimation is a way to get results when maximum likelihood craps out. That's the way that I think about it. Like it's also useful if you want to make up a brand new model and the estimation for it is something that would be very difficult to figure out in terms of all of the expected first and second derivatives to get everything that you need. So I see it as like a pragmatic thing. To the extent that you get different results from maximum likelihood, there are 2 potential reasons for that. One is because of the priors you chose. So you can end up with different results if you use informative priors, and then you'd have to have a basis for defending that choice. The other is because of what is outputted as a summary statistic. So particularly for random effects variances, the mode is what maximum likelihood goes for, like the most likely value. But when you do a Bayesian analysis, they often provide you with either a mean or a median of a posterior distribution. Well, if you have variances, those things are going to be positively skewed. The mean, median, mode aren't going to put you on the same number. So you can end up with a different estimate of your variability because it's a different measure of central tendency. So then you're sort of confounding the presence of prior information with a difference in central tendency of how you're reporting your results. And so then it's like, I would say be clear in what you did, create supplementary materials that have syntax and output for maximum transparency, and be ready to defend your choices. That covers everything. Anywho. I once just a few months ago, I had a paper that I helped with where one of the reviewers insisted that I had not done a multivariate multi-level model. And they were like, you should look at this textbook. I'm like, I followed the textbook. So I made a supplemental materials thing with the equations and the parameterization and all of that. And they were like, I don't think it's multivariate. So I'm like, damn it, it's multivariate. And I fought and I won because it was. So for more information about that, come to my longitudinal class. Because I had longitudinal outcomes from 3 different conditions where each person had multiple outcomes per condition. That's multivariate, that's multi-level. Anywho. Any more 3-beer questions you want to get me in trouble with?
Not a 3-beer question, but a quick question nonetheless.
Okay.
Can you explain the difference between mixed model and a multi-level model? I think they're the same, right?
They are the same.
Different names for the same things.
Yes, they are. Mixed effects is a term that means you have both fixed effects, which is what we call intercepts and slopes normally, and random effects, which are intercepts and slopes that vary over sampling units. So mixed effects models are the same thing as multi-level models, are the same thing as random coefficient models, are the same thing as hierarchical linear models, or HLM. All of these are the exact same thing. It's just different traditions and how they get described. Mixed effects models are often written as a single composite equation with fixed and random effects in it, whereas multi-level models have a layered system of notation that became popularized by Breik and Radenbush, particularly in the context of education. But it's just a way of talking about the model. It all collapses into one equation at the end of the day. So yes, if you talk to Ariel, he'll tell you mixed effects models or mixed models. If you talk to me, it's multi-level models.
And I guess the most decked out version would be generalized mixed model, right?
So there's linear mixed effects models, and then there's generalized linear mixed effects models, and yes. Yeah, so generalized would tack on link functions and non-normal conditional distributions in addition to fixed and random effects, and then you've got everything. Oh, and by the way, random effects are the exact same thing as latent variables. So all of your psychometric analyses, item response models, confirmatory factor models, etc., those are multi-level models. Everything is a multi-level model. What else?
Would it be incorrect to say that generalized linear models is like the classic trying to shove a triangle block through, like if you didn't do a generalized model, you're trying to shove a triangle block through a square hole, so you're doing things to make sure that it just goes smoothly?
Are generalized models trying to fix the problem of shoving a square block through a round hole or something like that? To some extent, yes. Okay. However, there's an article I put on your reading list on purpose because it has an alternative perspective that basically normal's fine. It's a simulation study that demonstrates that if you pick the wrong generalized model, you can end up worse than if you just said normal's fine. They also focused on the problem of correlated residuals, which is a separate issue, which we will tackle to some extent in this class. But yeah, I mean, at the end of the day, you don't know the right answer. So you're just trying to make the most informed choice and also potentially to see how much your results depend on your choices. I would feel much better if you end up with the same discussion section, regardless of what the exact permutations of the model are, versus you end up with a completely different story. Okay. So are we done with the quiz then? Formative assessment? Any questions on this? We're done with that? Okay, shutting that down. We got 15 minutes left to talk about quantile regression. That's what we have next. Shall we turn the page on that? Do that? Sound good? Okay. So I'm back in lecture 4 then. So this is one that doesn't have distributional assumptions, by the way. Go ahead.
What is the difference between the log normal and gamma distribution, and where do you have to use them?
There are two different distributions, both for positively skewed continuous data. Neither includes 0. So I would view them as two alternatives. Log normal is harder to find, but if you log your outcome, then it works out to be likelihood equivalent. Everything is exactly the same if you just log your variable as if you fit an identity link with a log normal residual.
Nice.
Yep. Okay. So the last piece of this then, an option that to me fits into this class, but it's not a generalized linear model. It's called quantile regression. And it's designed for continuous outcomes where you're worried about extreme values, having leverage on the solution, so outliers potentially dragging the slopes around. And it's also useful if you want to predict different regions of the distribution rather than just the middle. So I'm on slide 10 here in lecture 4. No, I'm not. I'm on slide, wait, here I am, on slide 17. That's where I am. A better way of handling outliers. That's where we are here. So regular flavor linear regression, general linear models, we predict the conditional mean of an outcome. The switch here is, rather than predicting the mean, to predict the median or some other percentile instead. So the way that it works under the hood, what normally shows up with respect to your model solution are the parameter estimates that minimize the sum of squared errors. So that's the idea of ordinary least squares, or the right answers for what the intercept and slopes would be for your fixed effects are those that make the collective E variance the smallest. Minimizing the sum of squared errors is the same thing as maximizing the likelihood. It's the exact same idea. Did I put the Ender's book on your reading list? I feel like maybe I did. I put it on all my classes. There's Ender's Missing Data book, chapters 3, 4, and 5 describe the relationship between least squares and maximum likelihood in the clearest terms that I've seen. So I tend to put that on all of my lists. But he talks about shows the math where they work out to be the same thing. In particular, residual maximum likelihood works out to be exactly the same thing. Maximum likelihood is the divide by n rather than n minus k version. So we end up with getting a residual variance, and we use that residual variance in regular general linear models to compute standard errors. So general linear models have distributional assumptions that allow us to create the standard errors, but the slopes are the slopes. So the difference with quantile regression is that rather than minimizing the sum of squared errors, it minimizes the absolute value of the errors, which is a function that in math terms is very pointy. It looks like a V. So it's not differentiable, meaning you can't use calculus to figure out if you're getting to the bottom of it in the same way that you can the minimum of the sums of squared errors, which has a quadratic type of shape to it. So that means that there's no easy process to get standard errors, but then you're also not making distributional assumptions. So it uses a combination of this criterion are how you figure out what the slopes should be, and then it uses some kind of iterative resampling procedure like bootstrapping to figure out what the standard errors should be. And bootstrapping, if you haven't heard about that, is the idea of sampling with replacement from your data, estimating the model, doing it again, estimating the model, and then pooling together all the different versions of the results that you got across your bootstrap samples. And then you find like the mean of all those things, and you call that your estimate. And then you can figure out what the empirical standard error would be, or confidence limits would be, given the results of those repeated samples. One thing that I mention is that if you want to use bootstrapping and you want to make sure that you get the exact same answers back, you have to set a seed. So a random number seed helps us control the randomness so that you can get it back again. For instance, in the homework system, the way that it works is that each of your ID numbers is the random seed that generates your data set. That way each student has their own unique set of answers. And in my examples, I am using a random seed, which is Jenny, Jenny, who can I turn to? It's an 80s song. 8675309, 8675309. No? Yeah. Okay, you gotta look it up. Look it up on the YouTube. So Jenny is forever my random seed in all of my examples. The one catch to this, though, is that it doesn't solve the independence issue. So we're still working with combining data across people, assuming that people are independent. There are multi-level versions of quantile regression, but I haven't seen a lot of them in use. So in SAS, I'm going to be using QuantReg. In Stata, there are routines called SQReg or IQReg, and R has a package called QuantReg as well. So in addition to predicting the median, you can use this to predict any percentile. And the difference is it applies a weighting function to split the two residuals unequally, So you can prioritize like the 75th percentile versus the 25th percentile or something like that. And when you might do this in practice is if you're interested in predicting different sections of the outcome distribution. So for instance, if I have an intervention that I'm going to examine, does it help students who are lower on my outcome more than it helps students who are higher? If I have a question like that, that's a reasonable thing, right? Because higher performing students probably have less room that they can grow. Most tests have some kind of ceiling effect. So you may see a stronger effect of an intervention amongst lower performing students. That would translate into predicting, say, the 25th percentile as opposed to the median. Likewise, if I were looking at something like response time in older adults, is age more related to response time amongst people who are slower than people who are faster? So people who are slower in response time, in which more is worse, would be, say, like at the 75th percentile as opposed to the median. So if you have research questions that are focused on, it's kind of like an interaction, but with the DV. Like, does the slope have a bigger effect on the lower section of the DV than the upper section of the DV? Then these sorts of procedures would allow you to answer those questions. So for instance, in the example that looks like we're going to do next time, I'm asking whether square footage matters more in predicting home prices if it's amongst the cheap houses versus the expensive houses. So are the same factors important in predicting house price amongst houses of various ranges in price? So that's the example that I have to go with. And then one last thing here, I've titled this Open in Case of Emergency, because I want you to be aware that there are other options that are not really model-based, that are more like Band-Aids, and you will see these mentioned in your textbooks as well. So you can ask for what are known as robust standard errors that are supposed to be robust to any conditional distribution misfit. So this is very commonly applied in the context of path analysis and structural equation models, where the packages may not have as many options for distributions and link functions. So you might have like an option, say in Lavon for R. Lavon has normal and it has ordinal, and that's it. So if you have something that is not one of those two, you're kind of out of luck. But what you can ask for are robust standard errors. So there's an estimation called robust maximum likelihood. That's what it's called in M+. That's also what it's called in Lavon. There's an empirical option that you can add to proc mixed or glimix. And Stata has several different options for robust standard errors as well. So in addition to corrections for non-normality, you can also do bootstrapping, jackknifing, resampling. That's resampling where you leave one out. There's various ways to test, to basically to try and make sure that your standard errors are not dependent on assumptions that do not hold. So these are tricks that you can use in addition to generalized models or instead of. There's some debate as to whether or not small samples work adequately with them. So I tend not to do this, for instance, in my longitudinal class, because a lot of times we don't have a lot of people. But it depends on your software what exactly it does. So this is a case where I would say check your documentation, see what the choices are, and then you can see what might work best for a particular problem. One thing I want to caution you about, though, is that this sort of fix, some people mistakenly think can apply to multi-level models. So within this same section, you'll see wording of cluster corrected standard errors that's supposed to fix dependency in the same way that they're supposed to fix non-normality. And for those of you who've been through any of the multi-level classes, what you would end up with are correct standard errors to incorrect fixed effects of level 1 predictors. So let's say that you have something like time within person as a context for longitudinal data. And if I want to look at the relationship between, say, perceived stress and well-being, and I ask people every day for a week how stressed you are and how good do you feel? At the person level, some people on average are going to report more stress, and some people are going to report greater well-being or worse well-being, right? So those are sort of cross-sectional differences that would be there all the time. That's one potential way that stress and well-being can be related. Within persons, Some days are worse than others. So within persons, like relative to your own normal values, is today relatively more stressful or relatively less stressful? And does that translate into relatively better feeling or relatively worse feeling within persons? That's a separate, distinct relationship between stress and well-being. If you fit one regression model where you dump all that data together, then the relationship that you get between stress and well-being is going to be a mixture of what it is at the person level and what it is at the day level, weighted by the amount of information available at both. So it's literally mixing two variables together and estimating one slope for it. So these techniques will get you the correct error, or the correct standard error for the incorrect slope. And that's why I don't do them. So I would caution you against thinking that dependency can be waved away with a simple fix to the standard errors, because it's absolutely not the case. Every level of your analysis at which you have different types of sampling has different types of variability and different types of relationship. And that's what makes the mixed effects models and the multi-level models a lot more complicated to teach, because you have to get all of that going at the same time. So. There, 140. How are we doing?
Good. Can I ask a quick question?
Yes, please.
So, from what I gathered, what we can do with quantile regression is we can, instead of the conditional mean, what we can estimate is the conditional quantile of our TV, right?
Yes.
And then let's say I want to look at the 75th conditional quantile. I can also compare that to the 25th or some other quantile, right?
Yes. So you can look at like
yeah.
what the slopes are at the 75th, what they are at the 25th, and you can actually test the differences.
Oh, cool.
Yeah.
And would this again require some sort of type 1 error correction type thing, or can I just do it as usual?
I would say there's nothing special about it beyond what you would normally do for worrying about type 1 error.
Oh, okay.
So I don't do any of the like Tukey's and all that crap. Like, no, I don't worry about that. 1 in every 20 p-values is wrong. So to me, like, there's a more general strategy of lowering your alpha level or limiting the number of tests you do. I don't worry about correcting for pairwise follow-up tests in only that one particular context.
All
But
right.
yeah.
And for I guess multi-level models, these robust things, we should be careful with those, right? You said that they estimate the right SC for the wrong fixed effect. So is there like a fix for that, or is this as far as we've gone so far in statistics?
You got to fit the right model. So it's a different linear predictor that allows relationships between persons to differ from relationships within persons, the same as you would have relationships between clusters differ from relationships within clusters. It's just that some people use this cluster-corrected standard error thing as like a Band-Aid that's supposed to just fix the whole multi-level nature of the data, and it just doesn't. It doesn't solve the fundamental problem.
Got it.
Okay. Question?
Does quantile regression assume that the population is normally distributed?
No.
Like, so like the 75th percentile, oh, no, because that does, okay.
No, it just assumes that 75% of the data is behind you.
Okay. Okay.
Yeah, so since it doesn't rely on distributional assumptions because it uses bootstrapping to get the standard errors.
Okay.
It's still supposed to be for independent analyses, though. But yeah, we will look at the example for that next time. All right. Any other last-minute questions before we call it a Tuesday? Yes.
Yeah, what kind of link function do we use for quantile regression? Identity?
None. No link function for quantile regression, because the idea is that y is already continuous.
Okay.
And yeah, and you're not worried about skewness necessarily because you're not trying to capture the middle. You're trying to capture you're not trying to capture the mean. You're trying to capture either the middle or partway through whichever quantile you're interested in, or all of them. So that's the picture that I ended with last week. Where in SAS, you can ask, what is the slope at every single quantile? And it makes this nice little picture for you. Okay. All right, then it's 1:44, which means I stop talking. It's garbage day, which means I say, see you Thursday. Let me know if you need anything. Good luck with homework. Let me help if I can, okay? All right. Thanks for being here. See you next time.